So Daniel, how
the
did
first
you
question
get
is going to
into
seem
your
very
field?
silly.
It's an exciting
Why are you
field.
interested in
Did
astrobiology?
you see it coming?
That's one of the biggest questions
So
we
actually,
can ask
yeah,
in science. Why wouldn't anyone be interested
when
in
I
it? But why
started
did you
to study, I
particularly
studied
get
physics,
interested in this subject?
and I was really interested
that's a great question, and
physics and astrophysics
in fact,
in general.
astrobiology
And
is
back
really
then when I
asking some of
started,
the
it was not
broadest
so long ago,
questions
but
humanity
I
can
started to
ask.
study at the university
and
around
I
95,
found
and
that many of
that
the
was the time when the first
aspects of
exoplanets
the
have been
rapid
discovered, but
development
it
in
was still a
astronomy
very
that we are
exotic and
witnessing are really playing a central
very
part in
small
answering
field
these
too. There were
questions.
very few people who have
And,
been working on exoplanets,
I
and
found
actually
also
didn't
many
get
of the
me
other aspects
excited
very
right away.
interesting.
And
So some of the key questions that
as
astrobiology is
more and
trying
more
to answer
planets
is
have been discovered, and
is
we
really
understood how
where is
different
life
those worlds
coming
are
from?
from
How did it
ours.
emerge?
I think it became apparent for
And
everyone that
is
this
there
is
life
something really
beyond
exciting.
Earth in
And
the solar system?
so when
and there are other stars?
when I had an
And finally,
opportunity
what is the future
to
of
study
life on Earth?
about exoplanets and
So
start to
that's
work on that
interesting
field,
that it
I
has a
actually jumped on the
terrestrial and
opportunity.
inward-looking component.
So just
I mean, maybe
remind
talk about
us,
that part because that's a little more surprising.
why people were so surprised. I
astronomers
mean,
care
the
about the
discovery
future
had
of
been
life on Earth.
anticipated for decades. It was incredibly hard to do it.
Yes,
and then,
it's an important part of
suddenly it's like
astrobiology
we don't
because
know anything.
I think there are
That's
so
right.
many
So
lessons
people
that
have
we can
been
learn
fascinated
from the
with
past. Evolution
exoplanets,
of
obviously,
life,
for a very long time, starting from the
and also the
Greek
correlation
who
of
have
life
been
and Earth.
thinking about
That
whether or
is
not there are
an obvious thing to
planets
apply
like
for our
ours
future
in
and
the,
better understand
in the
our future.
universe.
It's also, I think, a very important component.
But it's very difficult to find these
in
objects,
astrobiology
especially if we
understand
take the
how
solar system as a
interdependent
template, which
species
is
are
what
on other species,
astronomers have done, and
in
that's
the
for the
biosphere
reason
and
that
also of the planet
that was
itself.
the only
So
system that
we
we
often
have
think
known.
about planet Earth as
Planets
completely
like Earth
decoupled, a
are very
stable
difficult to
environment in which
detect, and
life can do whatever it wants to do. But in fact,
it's
the
only
reality
becoming
is that
now possible
life
to detect
is very much
Earth-like
coupled
planets
to
in
the
larger
atmosphere
numbers.
of Earth, and so
there
they
were
interact
many attempts
very,
to detect planets in
very
the past
strongly.
century, and
So
there
our
were
future
claims
really
actually going
depends
back
on
to the
how we
1960s of
actually can
extrasolar planets or
work
other
with this
stars.
biosphere in which we are part of.
Most of the claims
course,
until
that's basically
1995
the,
turned out to be
the
false.
component that directly
These were
informs
all
us or helps us to decide our long-term strategy. But
techniques where
also
people
from
have
astronomy,
been
we
not
know
detecting the planets directly,
how
but they have
stars
been
and
observing
planetary
the star
systems evolve,
and
and
deducing
we know
the
that
presence of
Earth
a
is not
planet
as a
around the
stable
star
environment as it may seem
by,
just based on human
for
history.
example, the motion
And
of
this,
the
of course,
star,
extends to the
precisely
idea
measuring
of
the
the
motion of
habitable
the star, and
zone, which is
deducing
a
that
sort
there
of
may be an
strange
unseen
concept
body
anyway,
that
but habitable
moves the
zones
star.
evolve too, right?
That's right, yes. And
so most
habitable
of these
zones
detections,
are
because they are looking for very small
those
signals,
in the
turn
audience
out
who
to
may
be wrong.
not
And,
know it. Basically, the idea
for
behind a habitable zone
several
is
decades, this was a
that
field
if you have a planet,
that
you would
was
say
so
move
challenging
Earth
that very few
closer to the
astronomers have
sun,
tried.
it would
In
start
fact,
to
maybe
get
you can
warmer
even
and
go
warmer
further,
the
'cause I
closer
know
you
some
go.
of
And
the
actually, you
people
wouldn't
in
need
their
to
stories,
go
and,
much
you know,
closer if
it
you
was
would
it
move
was
Earth
perhaps a
just by a
dangerous
few
field for a
percent
young
of it
person to go into, because there were
closer
the
to the sun and
graveyard
its
of
current separation,
reputations,
you would
That's
start to
false
make
claims,
it
and so on.
That's exactly right. Yeah, I
uninhabitable.
think it was.
And the
And,
same way, if you would push it outwards,
it was easy to.
you
It was
could push
very
it a little bit
difficult
further out, but
to
soon it would
even
become
get to the
very cold.
precision where
So
you
that
could expect to see planets,
region, which
and it
is
was
where
very
the
difficult to
temperatures are
verify
just
that what
right
you
for
found
an
was really a planet.
Earth-like planet
And basically,
or a sun-like
as
star,
many
this is
claims
what we
turned
call a
out to be
habitable
false.
zone.
And of course, each of those claims
the
have always
habitable
been
zone
reported in
evolves
the media very
because the
broadly
star
because of the
is
excitement that
evolving. All stars
caused.
evolve
Any
slowly,
failure was a catastrophic failure.
when they are in the what we call the main sequence.
And then,
in
of
most
course,
their lifetime.
what gets
But at the
discovered,
beginning of their
you know,
life
this
and towards the end of
crazy
their
Jupiter-like planet
life,
on a
there is a very
4.5
rapid
day orbit. I mean,
evolution.
it's insane. It's
That's-
closer
And the
than
other thing
Mercury
you
whipping around
mentioned
a
that's
star.
interesting,
So
the phrase
the first one
co-evolution
is a
of
huge
the-
surprise.
the planet
That's
and the
right. So
biosphere.
that's
That-
actually the
that
field.
argument can be reversed.
There
'cause
were
that's in
competing
fact one of
groups
the
that
ways
were
we're
trying
gonna
to
look
find
for life
extrasolar
in the
planets,
next phase of
and
this subject.
That's right.
most
yes.
groups
So,
have used the solar system as a
terrestrial life, at
template, so
least,
they did not
is
expect any
shaping,
planets really close to the
Earth's
host
atmosphere.
stars. And in fact, in
Earth's-
some cases, the rumor
If
says
we
that
look back in time, we
such
would not really
planets have been
recognize Earth
seen, but they
during
were
most of its
discarded as
lifetime.
an
It looked
artifact
very
in the
different.
data because
The atmosphere was
astronomers
very
couldn't
different.
really believe that
The
they could be
composition
real
was
objects.
very different.
But one of
And
the
in fact,
groups, that's the
if we really
Swiss
had a
group
time
from,
machine and we
led by
could travel
Michel
back in
Mayor,
time, really most of Earth's history
took
we
the
would not
data
be
on
able
face
to really
value, and
breathe,
they realized
well,
on one
because the atmosphere was very
particular
different.
star,
Life
the
is
Pegasus
shaping the
constellation,
atmosphere of Earth,
that the star,
and it's shaping it in a
when
very
you measure accurately, it's
fundamental, important way. And we can use
velocity,
this fact
it seems to
actually
change
to
on
look
a
for
4.5
atmospheres
day period. So every
around
4.5
other stars,
days,
planets
it
around other
basically
stars with
describes a
atmospheres
small circle
that have an
that you see.
imprint from biological processing.
And there's an
And what
interesting
is so
cultural
special
aside on
about,
that
you're
because
talking
as I
primarily about
understand
the
it,
oxygen, the one
their
part in
research
five
field
of
was
the Earth's
close
atmosphere.
binary.
What's so special about
So
that
they were
ingredient?
familiar
So
from their
oxygen
own
is a very
research for the
reactive
cadence
gas,
of observation that
if
would
we
let
would
them
just leave
find
oxygen,
a hot Jupiter.
That's right. Basically,
on
they
its
used
own,
a technique that
and we would stop
was
the
developed to
biological
find
production of oxygen. Very
close
soon,
stellar
the oxygen
binaries,
from Earth would
stars
be
that are
removed as it's
orbiting
interacting
each other,
readily with
and
fresh
basically
rocks
just
that are
measuring the
exposed
velocity
by,
of one star and
geological
recognizing that
processes.
it's
So
regularly
that's really a
changing as
major
it's
thing
moving
for
around its
oxygen. And the
orbit.
fact that we
It's the
see
same
oxygen
technique then
is because
that they
we have
applied for
biology that is
finding plants as they
actively
got better and
pumping
better
out
in it.
oxygen.
And that's true for
And
many of the
oxygen is in
techniques
fact
that we are now
a
using
poison
for
many,
finding planets. Many of
many
these
species,
techniques have been in the past used
especially
to
the
study
anaerobic
stars
species
and
that
origin
originally
stellar
in the
companions.
early Earth were the
And
dominant life
as
form.
the numbers gradually, I mean, the excitement
throughout
was incredible in the field. And as
slightly
the
more than half
numbers
of
of
Earth's
planets found
history, there was very
increased,
little free oxygen.
did they
if
make
any,
more sense
in
or
Earth's
not?
atmosphere.
And
and
the properties
species
of the
that
exoplanets.
So they- the-
lived
I
back
think
then, of course, did
exoplanets
not
are really
require oxygen, and
incredible
most
in a
of them
way
it was
because
poison. So
they
about
really
2.4
defy
billion years ago,
our initial
cyanobacteria
imagination,
started
and
to
they
produce
really have
large
turned out to
amounts
be
of
so much more
oxygen,
diverse than
and in
anybody
about
would have
a period of about
predicted.
200 million years, they
That
radically
keeps the field
transformed
very
the
exciting. We
atmosphere
find
of
exotic
Earth, and that
planets
meant
basically
probably
every
the
week now.
largest mass extinction Earth has
And
witnessed. Most of the
almost
species
every single
were wiped
property you
out
can think
by
about
this
the planet,
poisonous
we
reactive
have seen
gas.
huge
This is something we
variations
now all
in
depend
it.
on.
So this is a
and
sort of
so
another
the
a
first
a
surprise
grand
was
scale version
for the
of natural
hot
selection
Jupiter
operating with microbes.
type planets.
Yeah,
These
there
are
is.
gas
That's
giant
exactly
planets.
right. I mean, it
Often
was
even
beneficial
more
for
massive than Jupiter in our
cyanobacteria
solar
to switch
system
to oxygenic photosynthesis,
that
which
are
can produce
orbiting
much more
very, very,
energy
very close to their
than the
host stars.
unoxygenic
In fact, so hot that
photosynthetic
the day side,
pathways.
the side
But
of
at the
the
same
planet that
time,
is
it was
illuminated
providing
by
probably
the
a very
sun
strong
is almost as hot as
evolutionary
a
advantage.
a
They were
cool
basically
star.
able to wipe out their
So
competitors.
that's one of the examples,
and,
but we
gain
have
a
seen
much
so many other
larger
examples
foothold in the early Earth.
for
And of
really
course,
exotic properties.
even on today's
Also
Earth, we also
temperature,
know
density,
of a bacteria
masses,
that metabolize methane
planets
and
orbiting
methane.
binary stars.
Does methane have a
really
potential
huge
role
planets
as an
very far
indicator of
out,
life?
or very small
So
planets very close
basically,
in. Planets that are
you
locked in a
could use
resonance.
different,
These are planetary systems where
markers
the inner one
as biosignatures.
can go
This
around
is
2 times
how we
exactly
would
on its
call a
orbit,
gas
while
that
the
is
outer one
present in
goes
the
around only
atmosphere
one
that,
time. And these are very interesting
life possibly,
systems
and
from planetary
methane is one of
dynamics.
these
And I
possible
guess one of the
biosignatures.
theoretical ideas that emerged
One
as
basically
these
the key
discoveries
idea
were being
behind
made
these
were that
biosignatures is
planetary
that
systems
the presence
are a
of
little
these
chaotic.
gases
I mean, they're
in
not
the
quite as
atmosphere
regular.
mark
Our solar
a
system seems quite
disequilibrium. They mark a
quiet
deviation
and calm.
from
Yeah,
the
well,
equilibrium state
we
of
can
the
be
planet.
fair. So the
And in the
solar
case
system
of
is really boring.
Earth,
I
the
think that's
oxygen
basically what's
is
emerging from
produced
these
by
systems
biology,
we
and
have
that's a
seen
shift
really
from the equilibrium. And
systems
methane,
that
is
must have
also
underwent much more
in the terrestrial
movement
atmosphere is
and
primarily
rearrangements in terms
by
of their
biological
orbits.
processes, but also there are a
than the
couple of
solar
abiotic
system.
processes that can
Basically,
produce methane, and also
we have very good models for planet
oxygen
formation
for that
now.
matter. So we really have to understand a bit
and
the
we can
atmosphere before we
predict
can
and expect how certain
blindly
types,
accept any
where
of these
certain
gases
types
as a
of planets
marker
form
for
in the
life.
solar
But
system.
some of
And
these are
we would not expect
can be very
very
suggestive,
massive
especially
planets
if they come
forming
in
very close
combination.
in. We know that
And so
every system
what
that
you're
we see
alluding
where
to
there
is
is
the
a
fact that,
Jupiter-like
you know, in
planet
this
or even
game
more
where this
massive,
is
very
probably
close to its host
the next
star,
stage in
must
the
have
search
started
for life
its
in the
life
universe,
way out
the
in the
data
outer
is going to
parts
be
of the
complex.
planetary
You have to
system,
model it.
and through
There's not a
interactions,
single, you know,
sometimes with
smoking gun
the
tracer
material
that
from
will
which it
tell
formed,
everyone
sometimes in
front page
interactions
headline
with
the
other
next day.
planets,
That's right.
it's made its way
In Star Trek, there's a
close
device
to the
called
inner
tricorder,
planetary system.
and that's
And these models often
enables the
show
Star Trek
that
crew to
planetary
scan
systems
for
that are
signs
not
of
as
life on other planets.
stable as the
remotely
solar
or
system, they
even
can
look for
undergo
life,
sudden instability,
close distance,
where
but
you can
unfortunately
think
NASA
about
doesn't
almost the
really
planetary
have
system exploding
a
as the
tricorder
planets
at place, although you can buy copies
kick out each
replicas
other from the
Amazon.
system.
Now, the
But
theory
we don't
and
even
the
really know
models
how
must have
such a
evolved
device would
as
work in
almost
the
as
first
rapidly as
place.
the observations, because as I
Detecting
recall,
life and
the
understanding where
migration
life is there
planets,
or
I mean,
not seems very
these properties
simple.
were not
We
really
think
predicted in
that
advance
just
of
by looking at an
1995.
organism, it is
That's
easy
right.
to tell whether
That's
or not
right.
it's
So the
alive. But
models
in
are
fact,
now very
many
good in predicting
organisms
what
are
we
very
have seen
difficult to
already, which are not
organisms or not.
the true
It's very
predictions.
difficult to
But
deduce deduce whether or not
really
they
what
are,
happened is that
really living creatures.
we understand
Even on
reasonably
Earth, we
well
can
how the solar
find
system
examples
has
where it's
formed,
very
and the solar
difficult
system
to decide whether or not something
is not one of the
is alive. And
really
there are
extreme
border
planetary
cases, and the
systems,
most notable
as,
example are viruses.
we are starting to see now,
which
and
they
we,
cannot
I think
reproduce
our
on
models
their
are
own, so
right,
you
but we
could
have
argue,
underestimated
and many
sometimes
do,
the
that they
extreme
are not alive because
range
they
of
do need
properties
other
that
organisms
planetary
to
systems
reproduce.
can form in.
And you may imagine
if you
how much
consider
more complex
those,
it is if you
then
try
sometimes
to
the
do
assumptions
the
that
same
we made about
exercise
the
on another
formation
planet
of the
hundreds
solar
of light
system
years away
break down
potentially.
when you have
So
planets
we
so
really
large
have, I
that they
think,
really thoroughly
a chance
influence
to
the
understand
material from which they
really
form.
robust
Then
major
the formation
changes caused
process
by life
can
in
be
these planets, such as the
can
oxygen in
go in a different
Earth's
direction than we
atmosphere.
envision.
A change
So it's
that
very important,
has
and as always in
fundamentally
science,
impacted the
to
entire
make
atmosphere of the
predictions
planet,
and then
it's
compare
really
that to
a very
observations, and then
robust,
revise your model. And again verify it with
impact
predictions,
of
and
life.
that's exactly what's happening
So
with
people are, of
exoplanets,
course,
but in an
now
extremely
familiar
fast
with the
pace. Basically, in
cavalcade
about
of
15
planets,
years, we
exoplanets,
have
and kept finding
we went
Earth-like
through
planets,
several of these
and they
cycles,
might
and
think that, okay,
we now believe we
got
have much better
dozens
models
of
than we
Earth-like
had
planets, now
15
soon
years
have
ago.
hundreds. Just go out and
with,
look for oxygen
a couple
and find life.
nearly a couple
So
of
give us a
decades
sense
of
why
data,
this is a difficult
has it been
experiment.
possible to
Yeah,
find
it's a-
true analogs of our
so,
solar system, boring system?
Detecting
So
planets
it's
has been
it's
extremely difficult. And
it just so happens
many
if you would look
astronomers, it was one of
in
the
a large
holy grails
say
of
large
astronomy,
audience in a
finding
football game,
planets
the
on
first
other
ones that
stars,
you
and
would spot
it
out
took hundreds of
individuals
years
would
of
be
trying
the
and different
most
ideas to come
strangest
up with the
people
techniques
probably,
and technology
with the
that
strangest
enables
clothes
us now
or the largest
just partly
persons
to detect planets.
those who
And,
are standing out of
the
the
vast
crowd.
majority of the
in
planets
terms of
that we have detected
finding
until
solar
now,
system
and that's basically just
analogs, that's really our
years, the
goal
vast
to
majority of
understand
these
how
planets
frequent is
have been
the
detected
solar system
indirectly. That means that we haven't
in the
really
universe,
seen the planets,
and
but we just deduce their
we have not
presence by
reached the
their
point yet
impact
that
on
we
the
can
star.
find
So an example
planets
is
as
that you may
small
look for
as the Earth,
a slight wobble
as far
of the
from
star,
the
and the stars
sun
would wobble
as the
because
Earth
there is
is
a planet
around sun-like
orbiting
stars.
them
But
and
we are
pulling them
getting
around.
very,
But
very
that,
close. So
even though
NASA
we know
has
that there
launched
is a planet there, it
the
doesn't
first
mean we
space
actually
telescope
have seen the planet.
dedicated
And
to
if we haven't seen
finding
the planet, we
exoplanets.
cannot really.
And
look
also,
for
you may not know
oxygen,
this, but NASA
in
has
their atmosphere. So it's a
over
very, very
2,000
small fraction of
space
the planets
telescopes
that we
of various
actually can
sizes, but
right
only
now,
one is really
start to
dedicated to
characterize
exoplanets.
in detail.
And that is the Kepler
And
mission.
the planets that
And
we
it's quite
can
a
currently
modest-sized
characterize in
telescope.
detail,
It is
they are
it's
still
actually a very
far
small
from,
telescope.
Earth.
By
And these are,
the
of
standard
course,
space
the
telescopes
reflected
go, it's
light
a
of
very
a
small
Earth-like
telescope.
planet from a sun-like star is one part in
And
a
I think
billion
Bill
or
Baruch said
hundreds
it's
of
the most
millions,
boring.
and the
He's talking about boring
separated
solar
close to the
system.
stars.
This is the most boring
Just
mission. It
making
just
this
takes a
image
picture every 6
alone
minutes
is
for
hard, let
years.
alone make
That's
It's the
right.
same
spectrum of it.
one part of
That's
the sky.
exactly right.
That's
We really
right.
need
It's,
special
it's
telescopes
basically you can think
dedicated
about
to
the
do
telescope
this
as a large
really,
tube
really challenging task.
where one end open,
and
where
it's,
the
it's
light
often
comes in,
compared to the
it hits
challenge
the
of
mirror
trying
on
to
the other side,
characterize
and all the light,
firefly
this is a
sitting
parabolic
on
mirror, it's a
light,
curved mirror,
house.
and it collects all the
And
light in one
it
single
in fact
point, the
is
focal point.
it's a good
And
analogy.
there are no
We
real
really
moving
are
parts in
looking
this
for a very
telescope,
faint
and
source
they really, the
next to
soul
very,
of this
very
telescope
bright,
is what is in the
star.
focal plane. What in the
Nevertheless,
focal
it's
plane,
not
what you
impossible
would
to do,
find is a
and,
large array
we
of
now
CCD
have figured
chips.
out
So these are
ways,
chips just like the
to
ones you have in your
suppress the
iPhone,
starlight and
but
look for
larger
faint
in
sources, the
size.
fireflies around.
And these
that
arrays,
bright
there are
light.
42 of those chips. They can continue
What
observing
astronomers
the
always
same
need are larger
roughly
telescopes. So this is an
160,000
example
stars
where you do
for
need a larger
years, as you
telescope,
said, Chris.
because
So,
even though we suppress the starlight,
otherwise
those
not
little
much else is
fireflies
happening in
remain
the
very, very
telescope.
faint. And
And
current
and
telescopes
in
that we have, none of these
work,
have
it sort of feels
been,
like the field
made,
divided into before Kepler and
optimized in
after
any way
Kepler,
for
because the
exoplanets,
numbers just went through the
exoplanet
roof.
characterization. In fact, most of these telescopes have been designed before exoplanets were discovered
How did it
at all.
make such an impact?
Speaking
so
about mainly
quickly?
Hubble and
So
Spitzer Space
it's,
Telescope, or the other large ground-based
yeah, so there
How
are
does
many
does that change
several
with
aspects
James
to it.
Webb?
So
Is that
I
got some
remember the
potential?
time not so
So
long
James
time ago
Webb,
when there were so few exoplanets that we all knew
again, a
all the
telescope
names
that
of
was really
exoplanets.
designed
It
to
was
study the high
5, 6, and then half a year later,
earlier stages
seventh
of
was
the universe, but
discovered,
it
and
was a
everybody was
telescope in
excited that
which,
the seventh
during
is so
its
different from
design
the sixth.
phase and construction,
And this
exoplanets
situation has
have
changed
been
completely
discovered, and
when
they
now
got more and more
exoplanets are
important
released
role,
often by hundreds.
in the mission,
So
and the mission is now providing
the
very
current number is,
exciting
I believe, and I have to
platform
check
for
it every day,
exoplanet studies.
that we have about
the
6
two areas where
to
James Webb
700
is probably
confirmed
going to
exoplanets,
contribute very
and more than
significantly to our understanding of
2,300
planets
candidates from
are the
Kepler.
formation
Kepler
of
has
the
released the last
planetary systems, so the
release
baby planetary systems as
was
they form.
400 new planet candidates.
James Webb will be uniquely
And,
capable of studying those baby
And what's
planetary
the-
systems and
what's
try to
that
figure out
distinction
what are the
mean? 'Cause it's
components
a lot
that
more
that's a good
candidates
point
than
into the
confirmed. Does it
forming
mean that they're
planets.
going to go away or
Organics,
they're not?
That's a very good point.
volatiles,
So
which are very
Kepler,
important for plants.
let me tell you a bit
In
how
addition,
Kepler
James Webb
works
will
to
also be
understand
able
this.
to study
Kepler
at least giant
is
planets
staring at
that
this
are
150,000
very
stars
exciting detail.
continuously,
And in
and
some
looking
exceptional cases,
for
in a
what
few
we call
cases,
transit events.
it may
And
provide us
transit event is if you imagine a
about,
planet orbiting a
more
star,
Earth-like
and
planets,
you
but
imagine
most likely
just
those planets will be
flying
still
around
many
the
times
orbit
larger than
and
Earth is.
moving in a position
And
where
what
you
about this? Maybe a
actually the
slightly
orbit goes
discouraging
in front
subject,
of
but
the
what
star.
about
So
other
in that
missions
situation,
from
you
NASA,
would
say,
see
'cause,
basically
NASA
the
has
planet
been the main funder
during
of astrobiology,
moving around its
really,
orbit,
in the federal
passing
landscape.
between you
Are
and
there
the
things
star.
on
And
the
when that
horizon
happens,
there?
the planet will
So
cover
it's,
a small patch,
there is
a small
an active
part of the
discussion
surface
in
of
the
the star,
community,
right?
and that's a discussion that has been
Kepler
going
is
on
so
for a
far
couple of
away
years
from these
in trying
stars
to figure
that
out
it
what
cannot
is the best platform,
actually resolve
how we
these
should
systems.
build
All
the
it
next
sees is
big
the light from the
telescope
star.
that would be able to search
But it
for
will
life.
see the light
And this would be
dimming
a
slightly
purpose,
when the planet
rather
is
than
passing
James
in
Webb,
front.
which is a general facility.
So
This would be
with this situation, basically,
to-
Kepler
right.
is looking
These
for these
observations are
faint
so
dips
difficult
that
that you
sometimes
do
they
need
only
to
happen once a year.
Design the
For example, in the
telescope for
case
this
of Earth, it
measurement.
would
It
happen
can
only
also do
once
some other
a year
interesting
exactly,
science, but the main goal
because of the 1 year
is
period.
has
So
to
Kepler
be
is looking for
basically,
these faint dips, and
the
it finds stars
characterization
that have
Earth's
these kind of
like
small
planets and
dips.
search
But
for biosignatures because the
when
measurement
such
is
a
so
star is
difficult.
found, then
NASA had
it's marked as a candidate
in fact,
for being a planet
people
host.
affiliated with NASA and
But
also
what
the
happens
University
is
of
that
Arizona and
there are a couple of
places
other
have been
strange
thinking on how to design
objects out there
such an
that
instrument
can
for
also
several
cause dips
decades
that
now.
are not
It's
planets.
not
So
actually
these
a
we
new
call
idea, but
astrophysical
we now
false
got
positives.
much closer
One
by
example,
knowing
the
how
simplest
exoplanets,
example for that is
look
that
like
if you
where they
imagine
are located,
two
how
stars
we can
that
search for
are
them. And,
also orbiting each other,
there
and
has been in particular one
during
mission
its
that has
orbit,
been
during their
actually
orbit,
designed,
basically one is passing in front of the
to
other,
some
their
level
light
and
will drop.
has been worked
So
on for
that's a much
several
larger
years.
drop, but if you would
so-called
see
tertiary
this star
pathfinder
in the
mission,
background of a much
about
brighter
9-10
star
years
in
ago,
the
this was a
foreground,
major emphasis.
so that would
of
be an
the
alignment of these
astronomical
stars,
community too, and the astrobiology community.
Kepler would not be able
But
to see
because
that
of
this
the budget
is
realities,
a
it
two
just has
system,
been postponed,
basically, but
and
would see the combined light.
there are multiple
So we would
groups
call
now,
those candidates. That's really the
advising
distinction.
NASA
Some of the
about
candidates will be able
designs
to
and other pathways how
prove
this goal can
that
be
they are
reached.
planets,
And of course,
but not all
astronomy
of them.
is
And currently we think that
international
about
in general,
90%,
and is this
maybe
a
95% of
priority
the candidates
you know,
are actually
European,
real
South
planets, but
American, other
there will be a
astronomy
few
communities?
percent
Is it gonna
always
be-
that we
It's
cannot
easier
be
to get the money together when you don't have to do it
we really are
yourself.
at about 3,000.
Right, yes, NASA and especially the
That's
European Space
probably
Which is,
Agency
it's
has
a pretty
been,
amazing to go
for
from 0
decades
in
partners in some
1994
of the
to
largest
3,000.
space
That's
missions.
right, and there's
For
no
example,
way
in
anymore to
Hubble,
memorize all the names.
Hubble is a
and
space
nobody
mission that
tries
is
it.
primarily run
And
by
I suppose
NASA, but
another
there's a very
feature of that
important and
success is
significant
that
contribution,
to make
about 10%
a newspaper
from the European
headline or
Space
story
Agency,
catch
and the
people's
Canadian
attention has
Space
to be pretty
Agency is also an
bizarre or
important
extreme or
partner.
interesting.
That's right,
In the
yes.
Hubble Space
And so
Telescope.
what is the,
That
let's talk about
enables
the
the whole
exotica
international
for a little
community
bit. What
was
are the most
beyond these
intriguing,
three space
in the sense of
agencies
being
to participate in
informative
the
as well
exciting
about
science.
how
So
things work?
it really
So there are
merges,
really
all
basically,
the brains
I would
that
say,
are working on
two different directions people
on
are taking in
Hubble
studying
science and
exoplanets.
combines them.
Now we have the
And
luxury
something
of being
similar
able
is probably
to
going to happen with this
select a group of
Planet
planets we
Finder
find
mission,
particularly
or,
interesting.
or its
The two
successor, or
directions
the new
that
incarnation
people are
of this mission
converging
as we
to
get
is
closer
one
to
of them is
it
to
really is a
search
challenge
for an
that is
analog
so
of
grand
Earth
that
and the solar system.
It really is meaningful
So getting
to
closer
combine
and closer to solar system
everything that humanity
configurations,
can
and that
put
also
into this
includes
mission,
searching
both in
for
terms of
analogs of
intellectual
Jupiter, for example,
capabilities
as
and
a
also
first step,
funding.
or
is,
directly
of course,
searching
a very
for Earth
important
like
component.
planets.
And
these
as
are
but as we speak, this hypothetical mission,
the
there's
process
no
is
launch date
showing
or
No,
concrete
it's
plan.
extreme planets, but this is something
that's exactly right. The tertiary planet finder
not extreme in a
mission,
standard sense,
there were multiple
everyday sense, but these are
working groups
exciting
that
systems because they are more similar to Earth.
came up with different
Another
designs,
direction is to
but
find
as
planets that are
there
as
was less and less money
different from the solar system
available
planets
in
as
the
possible.
projections,
And
that
so
mission
we
was
have,
put on hold.
I
The
mentioned
European
already,
Space
hot
Agency
Jupiters,
had a
and these
similar
are
mission,
extremely
which
hot
was called Darwin,
planets that are
and
often their atmosphere
also the
is
two
heated
agencies
so much by
developed these
the
plans.
hot
There
star
was an
that it's
idea to merge
blown
them
away,
possibly,
and they are continuously
in a
losing
more
gas,
advanced
and
phase.
some of them are
Currently,
sort of evaporate,
given the budgets, most of these
in a few million
actual
years,
building
at least in one
attempts
case.
or design attempts
Other
have been put
systems
on
that
hold,
we see
and there is more
are,
focus placed on
appear to
characterizing
be
existing
icy
or currently
worlds,
known planetary system,
ocean
and also
worlds,
developing technologies
in
for
some
enabling
sense.
the mission.
We
Right.
are
And
now
that- and
we have
that's, of
now
course,
entered
an
the
important
realm of
point
super
about a lot
Earths.
of parts of our
These are
field,
planets
the technology
for which we don't have an
development
example
is
in the solar
coupled so
system.
tightly with
They are
what
somewhat
you can do
larger than Earth.
scientifically that
Typically
it
have a
becomes
mass
very
of 2
important.
to 6 times
Yes,
Earth.
right. It really is.
And
Technology
these
development
systems,
is something
at least
that
the ones we have found
basically
until now,
enables
many
us
of them
not
have very
simply
low
enables us to do
densities.
things we
And
couldn't
the very
do
low
before,
density
but
means
it also
that they
enables
must
us
have
to do things much
lighter
cheaper than we
components,
thought we could
more
do in
lighter
many
components,
cases.
and
What
less of the
always
heavier
has
stuff
happened in the past
Earth,
is
and the
that
heavier stuff
there
is
were
typically
multiple
rock and iron in
groups,
Earth, and the lighter stuff is the
but also
atmosphere and water.
engineers
So
and
these-
So you can say
instrumentalists
that
who have
their
been
mean
working
density
together
is
to
less
push new
than
technologies.
rock,
And
silicate
many of
or
these
something.
technologies
That's right,
are not
yes.
simply only
that's-
useful for
and this is
astronomy,
exactly
but they are
what
really useful
you
for
can
a
measure,
wide
for
variety
example,
of
from these
applications.
planetary transit events. The depth of that event, basically the planetary transit by how much the star is dimming, is directly given by the relative size of the planet and the star, right? The larger the planet, the larger fraction of the star is covered. So that, if you know how large is the star, and we know stars quite well by now,
medical imaging,
if
for example.
you
So
measure
these are really
the depth of that dip,
this
that
technology
directly gives
development
you the
programs.
size
These are really
of
programs
the
that
planet. And we have other ways to
on
measure the
long-term,
mass of the
really
planet.
significant,
So just taking the mass
results and technologies that are widely used.
the volume
And they
of
also
the
enable
planet,
us
we
to do
directly
things,
end up with the mean
that
density,
we
and that's
could not
something you
afford
can
or
directly
we would
compare
not
to
know how
Earth
to do
or rocks and iron.
So let me get back
And
to the
that's, of
idea of
course, the basic
habitability.
of
So
characterization.
I mean, there's
So I
this
guess
traditional
for people who
concept that you
think that
describe,
Kepler has
and
just swept away everything
you know,
that
the
came
Earth is
before.
the prototype,
It's
of course,
important
as
when
it should
people
be.
for people to
I
remember
think
that it only
the solar
measures
system
size.
is
If you want
telling
mass,
our
you still
solar
have to go
system
to
is
the
sort of
Doppler
telling us
method,
that there's
which
something
is-
called this
That's
and you really
cryogenic
want both, I
biosphere,
guess.
the
In fact, how many
exoplanets of
exoplanets have
large
both?
planets, and
Have that?
there are plenty of
So from
places
the
where
Kepler
if life just
sample
needs energy,
currently, I
water,
believe
and
there are
organic material, they
about
exist
45 or
outside
so
of an
that
Earth-like situation.
had
So
transit
how do we think about that in
detections,
larger
and then
scale? Or are we just
RV
so limited in
confirmation.
what we can look at we
That
have
number
to
is
stick
set
the
to
Earth-like
increase.
planet
There
rather
is
than
a
sun-like star?
dedicated telescope
there
that
is
is being
that's an
constructed.
excellent
In fact,
point.
the
Yes,
telescope is
the
that
habitable zone,
instrument
which
is now
receives a
being,
lot of attention in terms of the
installed
habitable
in the Canary
exoplanets,
Islands,
is a very important
in the observatory,
guideline,
which will be dedicated
guiding
fully to
concept
follow
for
up
studying those
Kepler
systems.
candidates.
But it really doesn't mean that this
So that's actually
the only
Harvard,
location where we would expect
is
or could
involved,
imagine
Harvard
life
CFA, and
around
this
other,
is
stars.
a
And
copy.
a great
of,
example are the icy
the key
moons
here
in the
really is
outer
not so
solar
much the
system.
telescope, but the
For example,
instrument. The
Europa
instrument
or
is a
Titan.
very, very special
These
one.
moons
That's the
are
instrument
by
that a
any
Swiss
definition
group
they are
has
well
developed.
outside
Basically, the
the habitable
group is
zone, but they
a
and that
successor
means that
group
they
of
don't
what
really have
discovered the
enough
first
energy from the
exoplanet around
sun
the sun-like
to
star.
sustain an
And
Earth-like
they created a
environment.
precision
However,
Doppler
they
machine,
do
and what it
receive,
does is
for example, in
measures
the case of Europa, energy from
velocity
tidal interactions
of a star
with Jupiter.
in our
That
line of
means that
sight to an extreme
during its
precision.
orbit,
And
Europa is getting a little bit closer and a
that
little bit
precision
farther
is
away from Jupiter.
significantly less than a meter
and
per
as it
second
also
now, and that
turns
means
around,
that you
there is
can
a tidal
tell whether
flexing.
the star is
It's,
changing its
Europa is,
velocity by
squeezed basically as it moves around, and
speed
that provides
similar to your
additional
walking
heating.
speed. Actually,
So it's heated
less
from
than that,
inside,
which is
from
truly
its
incredible.
interior,
And
that
as an
allows
aside,
it
it's,
to be actually
as I
warmer
understood
than it should be, significantly
Kepler,
warmer.
Kepler clearly
producing,
can find Earth-sized
probably
objects and has done so, but the
underground
Doppler
or
method
under
is
ice,
challenged to find Earth-type radial.
So these are
reflex
environments
motions,
that
right?
That's
Can
right.
it do
are
it?
quite
Yes,
Can it
so-
get there?
Well, there's a
interesting
big
in
debate
terms
about
of
it, and
searching for life,
I
and
think
they
that the
may
people
hold
say
life that would be
that
probably
they can do it are
different,
right. And
significantly
let me give you
different from that
here
of Earth.
the
And
arguments.
this is an
for and
environment
con.
that is exceedingly difficult to
for a
study,
long
even
time,
within our own solar system. So there are ideas to
precision
send
by
probes
which we can
to
measure
Europa
changes in
and
the
some of
velocity
other
of a
icy
star,
moons,
which is basically
and
what you
we
are
have
looking
recently
for
landed on Titan.
when you want to detect
these
how
environments can be
planet
studied
is wobbling a star.
with
You are
great
looking for these
difficulty, but they
changes.
can be studied in the solar
That
system.
precision was
but they are
limited by
really
how
beyond
accurately
what
you
we
can measure the wavelengths
even
of light.
conceive,
So in a
um,
Doppler shift, right, when you're
study
looking for a
in
Doppler shift,
other
what you
solar
look for is
systems. So in
certain
other solar
features
systems,
shifting in
we would
wavelengths.
focus
Now, if your
on the
instrument
most Earth-like environments, while in our
has
solar
a finite
system, we can send planetary
precision in
probes and
measuring the
explore some of
wavelengths,
these
it's very
environments,
difficult to find
as
out
much as we can.
small changes, and
Well,
that was
let's-
exactly
so
the
that's
case.
a sort of thinking
Over
out of the
year
box and
timescales,
habitable
which
zone.
are
Let's
the
talk
timescales
out
you
of
have
the
to
box
compare
on
velocities
biology
with.
itself.
Many
and
things have
the
changed in the
biological
instruments.
part of
Temperatures,
astrobiology.
the air
I mean,
pressure has been
we
changing,
might look for metabolic
detectors have been
processes similar to
changing,
those that
etc.
happen on
It was
the
very
Earth.
difficult to
Oxygenic
keep those
photosynthesis, of course, it's a
constant.
great
And it's
biosignature.
perhaps no wonder
Is
that
that
the
too
Swiss
limiting,
group
or do we know that life always has to work
have
this
used
way?
the traditional Swiss
No,
accuracy
we don't
in
know,
developing
and life
a
is-
machine that
has
is
been
superbly
I think
calibrated. So this is a
two
huge instrument that is
perhaps
sitting in
most
an
exciting
enormous
areas in
vacuum
astrobiology,
chamber,
at least from my
devoid
viewpoint,
of
have been
air.
the
The
exoplanet
temperature is
discoveries
stabilized
in
to
the past few years,
millikelvin level.
and the other
So-
has
So
been
big
what we
precision
learn
and
about
probably
life,
good supplies of
especially
chocolate
extreme life
nearby, right?
That's right, co-calibrated to a
biochemistry.
Swiss watch.
And
Yeah.
And
a very important
that,
part of astrobiology is
that
understanding
instrument and actually
the
that
extremes of Earth's
design,
life, terrestrial
which
life,
was
and
very
the
expensive
inner processes that
instrument,
enable
but
life.
turned
And
out to
we
be
have seen an
extremely stable
incredible richness and variety
the
in
accuracy
terrestrial
itself
life
now
that
is actually
far
not anymore the
exceeding
limiting
what
factor. We could
biologists would have
build
expected
these
and
instruments, and basically this is called HARPS. It has been installed in Chile.
So we find life
in producing large
almost
number
every
of
single
planets. A clone of this is
environment
now
where we could
installed in the Canary Islands.
possibly imagine to have life.
Earlier,
and some where we
what happens though is that with this
and so some of the
technique,
examples that are
people
in the headlines from
hit a barrier.
almost daily
They realize
are
that
finding life.
Even if they start to collect more and more data,
deserts,
it just gets difficult
Earth,
for
example,
certain
the
stars,
Atacama
actually,
Desert,
for most stars, to get to an accuracy below 1 meter per second. And that's really, if you speak about detecting an Earth like planet, you would want to have moisture about 30 to 40 centimeter per second accuracy.
Nevertheless, we do find
always,
which is 1 part in a billion. I mean, that's relative to the speed
in that
of light,
environment, or even in the coldest
it is an incredible
we find life, of course, in
achievement that
this
is possible. But what turned out to be the problem is that stars themselves,
and even inside the lithosphere, inside
are active. And so what we mean by active is that if you have ever seen the sun
the whole idea of
through
what's
a narrow
toxic
band
to
filter,
life is an interesting concept.
which you should not try, but if you have seen
really
images with professional narrow band filters, what you will see, it has a lot of structure in it. It's not
versatile,
it's very far from being a boring globe, but in fact you will see
the limits of terrestrial life is
granules and a lot of structure in it.
There are many teams
in these very tiny levels, the appearance and disappearance of those spots can change, can introduce basically an apparent shift in the velocity, just because one of the sides of the star is covered, which is turning towards you, while the other star is not covered by a spot which is moving away from you. So the shift between the red and blue shifted light
is an
from
excellent
star can be offset.
motivation behind
So
searching for
these
life.
minor changes that are really difficult to detect, but they become suddenly your limiting factor.
And
when
of
you are
course,
looking for
even
tiny
that is
variations
not jumping
induced
out of the
by
whole
Earth's
box, because that incredible
And I guess the only thing you have
metabolic
going for you
diversity
is
and
that
the
those
microbial
sort of
diversity
changes
of
in
the Earth is still
stellar
one
atmosphere,
genetic template, one
I presume you
version
can time
of
average
life.
out, because you're
And
looking
I
for
suppose
periodic
people say
data.
that, like
you are
Titan,
completely right. So
the
that's basically
chemistry
the
is
big
different
debate.
enough, it might
And
be a
I think
completely different
that you can
basis
actually
if
average
it
these
were
out.
possible to have
Some
biology.
people argue
That's
that
right, yes, in
because
Earth, I mean,
these are not
it's
randomly
always amazing
distributed,
to me
but
that
then to
if
come
you
in
look through
cycles,
basically all the species, everything that we know, it really is
it
all
may not be
interrelated.
always
It
possible
really basically is
to
using the same genetic
average them out. But I think
template
the
and
initial
same,
tests that I've seen were at least confirming
a machinery
that
to produce and replicate
at least in
itself
a
and
number
carry
of
over
cases
the
you are able
information.
to average them out. So I
Although
think
almost
that's-
every other
that's
property of
the
life has
optimistic
changed, that very basic,
outcome,
that
and I think
real
that's the
core
one we are going to
has
see.
remained constant
And of course,
throughout,
that number
Earth's,
you gave of
history, at
Kepler
least as much we know.
planets
There are
with
ideas
Doppler
that
measurement
there
as
may
well,
be
which is
what
quite small.
people call a
And
shadow
the other
biosphere.
thing everyone
Uh,
forgets is that the
the
Kepler
idea
stars
is
are
that
faint.
this,
They're making it hard. I mean, the
genetic,
ground-based observers
alphabet
would rather
that we
look
are
at a lot brighter stars
all
than 14
biological
magnitude,
systems on
15
Earth that we know
magnitude.
And
are
that is
using.
that
It's
is
just one
exactly
possible solution of the many possibilities that
one of
could have
the
occurred.
next
There are,
challenges we are facing.
attempts,
So Kepler
actually
is
successes
designed
to use
to
to
answer
extend
really
this
one
alphabet
question,
and make
and everything
synthetic,
else that comes out of Kepler is just bonus science.
genetic code.
The question
which
Kepler is
can
answering
also be shown to
is
work reasonably
how frequent
well.
are
So there are other
Earth-sized planets around
It's nowhere
sun-like
written that
stars
this
at one astronomical
exact
unit.
setup
Okay?
is the optimal
It's finding
or the
thousands
right
of other
setup. So
planets, but
people
that's
rather
not
think
the
that
goal.
this was
It's also
an
presumably
experiment
going to give a
frozen in
great
time.
size distribution and constrain the
People
models
often
of
think
how
that there were
planets
multiple
Yeah, that's right. So it really is revolutionizing our
types of life
understanding
that
of plant formation and exoplanet properties.
One of them, the
But
most
it really is
successful,
geared to do that.
has actually, as soon as it was successful enough to robustly replicate and diversify, it was able to overtake Earth, and basically all the competing life forms were pushed to extinction.
And this is, of course, a very difficult hypothesis to test given how little traces we have of the early Earth.
That's right. Basically, life is extremely good in using everything that is available. So we expect that all the other alternate life forms would have been eradicated. So we don't expect to find anything from them unless they somehow stayed alive. And that's the idea behind the shadow biosphere. There are attempts to try to find in some isolated pockets, in some really extreme environment on Earth, some other type of life that may be lurking in the dark that we have not seen until now. It's a very difficult hypothesis to test. We never know when we checked every location where it's possible. So it's difficult to come up with a negative result and say that we have in fact not found anything. So we learn that there is nothing like a shadow biosphere on Earth. But nevertheless, it's a very exciting possibility that in fact, if we do find a life form, it would be of course extremely interesting for us.
Now, it's not a full version of that experiment, but it's very exciting that I think just in the last year the Russians have broken through to Lake Vostok, which is a sort of was been sealed off for tens of millions of years, I think, from the That's maybe not enough to expect some alternative, but there could be organisms that are unknown elsewhere.
Yes, exactly, and that's also an example of independent evolution. So we would be able to, once that lake is actually properly explored and we have samples that are not contaminated also by the outside world properly sampled, we may be able to find examples of independent evolution from Lake Vostok. It's perhaps, who knows, we may be able to find an example from a shadow biosphere from that lake. What is difficult about finding something that is really not like our own well-known biosphere is that we don't really have the right tools to do that. So all the biodiversity studies that are currently carried out, for example, when they travel across the ocean, they sample water at different depths, in different longitude and latitude, and they use DNA sequencing to identify the biodiversity as a function of location and depth. All of these are only sensitive to organisms that we know. We would not be able to find, even if our bucket was full of different life, we would not be able to recognize it probably.
So these are, and basically it has to have nucleic acids, and you're sort of amplifying DNA.
That's right.
To detect it, these little microorganisms.
That's right. The biodiversity studies usually use a small fragment of the DNA that is highly conserved throughout evolution. And that is basically in an iterative process amplified. So even very small samples can be amplified by millions of times and then can be detected. But it already basically lies on one small fragment. Actually, in most cases, that's an RNA fragment that is present. So now, the other interesting thing is one may think that you may just scoop up, some dirt from the Atacama Desert, and you may be able to grow your own microbes and find out if they look just different. But the surprising fact is that biologists can grow only less than 1% of all the microbes that you could collect. So if you scoop up a little dirt and you try to culture those microbes in it, more than 99% of those will die, no matter what you try to give them as nutrients or what conditions you try to keep them in. We just always fail to culture them. So we really just see a very small fraction of the biosphere.
And then that's a sobering thought, that as we're busy looking for life beyond Earth, we don't fully understand terrestrial biology.
That's right. Yeah, it's an extremely complex process. I mean, we understand, of course, most of the main processes involved in biology that are shared, but in terms of the diversity, the complexity of biospheres, that is really fully unexplored, and I think provides a really exciting intellectual adventure.
So let me finish with, again, another big picture. The Drake equation has been used for decades to organize the information. I think Frank Drake even said it's a container for ignorance. But I mean, excitingly for us, the first few terms are being defined by astronomy, which sort of leaves the back end of the equation to be an issue. What's your opinion of SETI? Is that a worthwhile thing to do?
SETI is a very exciting enterprise, and I think it's let me give you pro and cons on these. So, of course, the pros are pretty obvious, right? If we do find actually a message, or even maybe not an intentional message, but just a radio signal that indicates the presence of another intelligence in the galaxy, that would be one of the most fundamental discoveries of human society. It would really be a pretty fundamental discovery that would provide us with insights about our location, in space and time, and would give us a different perspective on who we are and where we come from. So that it can also have possibly further advantages. I mean, you could imagine that kind of messages would enable us to develop new technologies, maybe even communicate with them. If we could actually decode the message, respond, and maybe it wouldn't take thousands of years. If we find a civilization very close to us, that would be great. So this is a very exciting and potentially really high payoff enterprise. The problem is, of course, with SETI is that it has been tried, there's just so much left to do, and it's very difficult to know what would be the end result. When is the experiment complete? So many...
and you're talking about something fundamental in science, is you have to be able to explain a null result. You couldn't get money out of the NSF or anyone unless you said what it meant if you found nothing.
Yes. So you really want to design, anytime when you do science, you want to design experiments that are really well defined. They have a clear question, and in the end, ideally, you get an answer, yes or no, or you measure something. And questions that are defined in this way, traditionally in science, have been the ones that were really providing reliable progress. There are some other questions, of course, discoveries and chance discoveries that were very important, but in terms of programmatic science, you do want to define experiments. And a difficulty with SET is that the parameter space is just so large, and our ability to scan it in terms of, and I'm thinking about how many stars there are in the galaxy, what are all the possible frequencies and polarization directions and type of encoding you may look for. That parameter range is so huge that it remains very difficult to scan a large enough fraction of that we could interpret the result unless we find something. So that has been one of the challenges that SETI research has been facing, but nevertheless it hasn't encouraged many people, and there's a lot of excitement also in part reignited by Kepler to continue and extend the traditional radio wave SETI research, and there are exciting projects run at Harvard and Berkeley, for example, that use optical telescopes to look for optical SETI. It's a new type of SETI research.
Mm-hmm. Okay, that's great. So I got to finish with an obvious question of, what does your gut tell you? Is how abundant is life in the universe? You don't think we're it, right?
I would,
let's not even, separate it into the microbial or any kind of life and maybe advanced life. What do you think about life of any kind?
I would guess that based on what we know, probably at least microbial life would be quite, I could imagine it could be quite frequent in the galaxy. We now know that every star basically has multiple planets. Many of them are in the habitable zone. Many of the planets are similar in size and probably in other properties to Earth. So Earth, the more we know about exoplanets, the less exceptional Earth looks. So based on that, and also the extreme conditions in which we find life, I think it's a good guess that microbial life could be very frequent in the galaxy. The big question then after is whether or not intelligent life is common, and that really depends, I think, on how good is intelligent life in ensuring its longevity. So how long will the human civilization last? Is it comparable to the timescales you need to send a message to the other side of the galaxy? If yes, then intelligent life should be frequent. If not, then probably not.
So you're alluding to an important thing, that in astrobiology, the real estate of space is the one we're familiar with, but there's also the real estate of time, which is just as important in terms of what you might detect and the stage of its evolution and so on.
That's right, because the finite speed of light that we can communicate with, it can take hundreds of lights to send messages even to the most nearby stars. And if we want to communicate across the galaxy, we are speaking about lifetimes, about travel times about 100,000 years, especially for sending messages there and back, which would mean the real communication. These are timescales that are much, much longer than human civilization, or really the timescale over which modern humans have existed. So in order for us to be able to, we could technically communicate with civilizations across the galaxy, but the question is, will we live long enough, and will they live long enough?
Okay, well, I think that's an optimistic way to end. So I hope we do live long enough. But I think you're pretty confident, it sounds like, that the agenda of detecting microbial life is maybe a few decades agenda that we might succeed in. I
definitely hope. Yeah. I think that once we have designed the next telescope that is really geared to do this, I think and if we do our job right, I mean, that telescope should be able to detect microbial life, and I would be surprised and disappointed if we wouldn't find several examples before I retire.
Right. Okay, that's great. Thank you, Daniel.
Thanks.